When people find out I'm an astrophysicist, they have one very big question for me. Do aliens exist? It's possibly the biggest question that humanity has ever asked, right? Like, is there other life out there in the universe? Are we alone? And while there's no scientific evidence yet anyway for life either in our solar system or beyond, science can help us estimate a probability or a likelihood that life exists out there somewhere in the vastness of space. Alright, so to answer this question scientifically, we first of all have to put an estimate on the number of stars in the universe that have planets that can support life. So where do you even start with that? Well, why don't we start with just the number of stars in the universe, first of all, and then we'll get to how many of them actually might have planets and planets that can host life. So stars are found clustered together in what we call galaxies. They're essentially islands of stars out there in the universe. Our galaxy is the Milky Way galaxy, in which the sun is just one star of 100 billion of them. So to work out an estimate for how many stars in total there are in the universe, you can start by working out, well, how many galaxies are there in the universe? How many islands of stars? And we can do this using the Hubble Ultra Deep Field. It's an image of a patch of sky that's less than 5% of the size of the full moon. It was taken by the Hubble Space Telescope, which stared at the darkest patch of sky that we know is in a constellation called Fornax in the southern hemisphere. And it stared at it for about 6 months total. And that was to collect as much light as possible from even the faintest, furthest galaxies that might be in that region of sky. This is what it found. You can see in this image that there's 6 stars from our own Milky Way in the foreground, kind of like getting in the way. But everything else that you see in this image is a galaxy, an island of billions of stars. From this beautiful spiral galaxy here that looks like the Milky Way to this tiny pixel, right, that's so far away we can barely detect it. At the last count in this image, there's about 5,000 galaxies in this one tiny patch of sky. This image is only 1/30th of a degree by 1/30th of a degree. The entire sky is a circle, right? It's 360 degrees round. So this is a tiny, tiny fraction. It is in fact only 1/24 millionth of a fraction of the total area of the sky. So if you take that 5,000 estimate of the number of galaxies in that tiny patch and extrapolate it across the entire sky, then the number you get is that there are at least 100 billion galaxies in the observable universe. But remember, the Hubble Ultra Deep Field is the darkest patch of sky we know that has the least amount of stuff in it, therefore the least amount of stuff that's giving off light. So 100 billion is probably an underestimate because there's also galaxies that have smaller dwarf galaxies orbiting them as well, like the Large and Small Magellanic Clouds, the little dwarf galaxies that orbit the Milky Way that you can see from the southern hemisphere. So perhaps we should round up our number to at least 1 trillion galaxies in the universe, just to be safe. But then the question is, well, how many stars do each of those galaxies, those islands of stars, contain? The Milky Way, for example, has around about 100 billion stars, but its largest closest neighbor, Andromeda, has 1 trillion stars. There are also the smaller dwarf galaxies though, and the huge elliptical galaxies with even more stars. So let's assume that the Milky Way's 100 billion stars per galaxy is a nice sort of average amount of stars that you would get per galaxy. Then you say, okay, there's 1 trillion galaxies, at least in the universe. Each of them contains, on average, about 100 billion stars. You get the number of stars in the universe is somewhere around 100 sextillion stars. That's a 1 with 23 zeros after it. It's a big number, one that's really quite difficult to actually imagine. Like even the analogy that people use with time to demonstrate, the difference between 1 million and 1 billion, like even doesn't help here. So if you haven't heard this before, 1 million seconds is 12 days. 1 billion seconds is 31 years. 1 trillion seconds is 31,000 years. And 100 sextillion seconds is 3,100 trillion years. So it's an unfathomably large number. Despite its ridiculously largeness, we at least still have a number now for an estimate on the number of stars in the universe. The next question is, how many of them host planets that can support life? Now we think the majority of stars probably do have planets around them. It's sort of like a natural occurrence from the formation of the stars that you will end up with the leftovers, the rubble going into forming planets around them. That's a fairly recent sort of understanding from the fact that we've just found so many planets around other stars in our Milky Way as well. But will they support life? Are those planets that form actually habitable? That's the bigger question. Now, the first thing you need to get life is the ingredients for life. Things like carbon, nitrogen, oxygen, the stuff that makes up you and me, and proteins and amino acids and all this kind of stuff. Those elements are made in stars themselves. Unlike stars, which are mostly made of hydrogen, they turn that hydrogen into helium in nuclear fusion. When they reach the end of their lives and go supernova is when they produce the heavier elements in nuclear fusion. They're almost forced to as they try and resist the crush of gravity inwards. It's why you hear people say, like, we're all made of stardust very poetically, right? It's because all the elements that make us up, like all the elements that go into my hand right now, they were all forged in a star that is now long dead, and that the sun and the solar system formed from the remnants of. So you only get planets that have the ingredients for life in regions where many generations of stars have come before. For life to develop, you then need time, right? The Earth and the Sun are about 4.5 billion years old, and we think it took just less than about 1 billion years for the first signs of life on the Earth to appear. Then took another 4 billion years or so for life to fully evolve into intelligent life as humans, right? So you need a really long time. You need a star that's going to live at least 1 billion years for life to appear on that planet. That rules out the most massive stars, right? They have to burn their fuel quicker to resist the crush of gravity, and the most massive of them only live for 100,000 years or so. So that rules out a good chunk of our 100 sextillion stars that we reckon are in the universe. And it also rules out the ones that are like first generation stars still, like the ones first form out of pure hydrogen. We need the third, the fourth generation of stars that have formed from the leftovers of others to have the ingredients there that are going to live the longest amount of time to give life enough time to develop. Of the stars we're then left with, which do have planets, those planets need to be in what's called the habitable zone, or the Goldilocks zone. You know, where it's not too hot and not too cold to support life. And that zone will actually move depending on how hot the star is. So hotter stars are bigger and the zone will be much further out, whereas if the star is smaller and cooler, you can have the zone much further in. You can have a planet actually orbiting quite close to its star where it would still be habitable, whereas, if in the solar system, for example, Mercury is far too close to the sun to be habitable, right? It gets absolutely fried by radiation from the sun. But if the sun was much smaller, then maybe Mercury would be habitable because it would be cooler as well. So actually getting a planet in that zone, that reduces your probability even more that a star actually will have a planet that can host life. So if we take a very conservative estimate for all of these numbers, reducing our probability all the time that a star will have a planet that can host life, and I actually go through all those numbers in chapter 8 of my book as well, if you're interested in picking that up. But if you do that, you get a probability of 1 in a quintillion stars having a planet with both the ingredients and the right conditions for life. That's a 1 with 18 zeros after it. But because our estimate of the number of stars in the universe is 100 sextillion, and that 1 in a quintillion of those supports life, even if you take a really pessimistic view of things, you still come to the conclusion that there are 100,000 planets out there in the vastness of space, in the entire universe, that could support life. So to me, as a scientist, looking at all of the statistics and the probabilities, the question of do aliens exist is a no-brainer. Yes, of course they do. Space is so vast. There are so many stars out there. I think it's very, very unlikely that we are indeed alone. But these are planets probably in other galaxies entirely, billions of light years distance. Travel and communication with them would be impossible under the laws of physics as we understand them. If we're to think about life on habitable planets in our own Milky Way galaxy that would at least be a little bit closer to home, we perhaps have to take a more optimistic view. This is what Frank Drake did, the famous astronomer, when he came up with the Drake equation, to actually try and estimate not just the number of habitable planets, but the number of planets with civilizations that were capable of communicating with others. The kind of things that like sci-fi writers dream of. And the equation looks fairly complicated. There's lots of different terms, but they're all ones that I've sort of spoken about in this video so far as well. Now, there's a huge uncertainty on all of those terms in that equation. There's a huge range of different values that you can assume for each of those terms as well. So there's a huge range of values that you can get using this equation for the number of active, communicable civilizations in the universe, right? And it goes down from like the tiniest of fraction, which would mean we're alone in the galaxy, probably even alone in the universe, up to 15 million actively communicating civilizations in the Milky Way alone. But of course, it's once again the scales that scupper us, because the Milky Way is 100,000 light years across. That means that it takes light traveling at the fastest speed there is, the universal speed limit that Einstein said that you cannot travel faster than, at least as we understand the laws of physics right now anyway. It takes light 100,000 years to get from one side to the other. So if you were going to send a radio signal, which is light, it would take 100,000 years to get to a planet on the other side. Not exactly a timescale that lends itself to having a conversation. We're not even close to sending a probe at even a fraction of light speed. The furthest thing we've ever sent from Earth are the Voyager probes, which were launched in the late 70s. They've only just left the solar system. It will in fact take Voyager 1, which is the furthest thing currently from Earth and the Sun, 75,000 years before the Sun is no longer its closest star. So while I firmly believe that life must exist somewhere out there in the vastness of space, just because the numbers don't lie, I think the sheer scales involved are really going to scupper us when it comes to any form of interstellar travel or communication. And I don't think we'll ever make contact with another intelligent alien civilization. But I would be very happy indeed to be proven wrong. Before we get to the bloopers, I just want to say a huge thank you to this week's video sponsor, Brilliant. Brilliant is a website and an app with a huge range of interactive courses on topics in science and maths that get you to learn by doing. Now, you wouldn't be here on my channel if you didn't want to learn something new, but maybe you want to take your understanding to the next level. And personally, I think Brilliant is a great way to do just that, especially because recently they've upped the interactivity on their courses, making them so much more intuitive. For example, check out their logic course. One of the skills you need as a scientist is critical thinking, especially through mathematical reasoning, right? It's how you work through probabilistic answers to questions like, do aliens exist? In Brilliant's logic course, you can learn how to solve problems by going through logical reasoning, like I do every day working through questions in my research. So if that sounds like fun to you, maybe you're a budding scientist too, then head to brilliant.org/Dr Becky and sign up completely for free. Plus you'll get 20% off an annual premium subscription if you go to that link, which is linked in the video description down below. So a huge thank you to Brilliant for sponsoring this video. And now, roll those bloopers. Oh, it's so cold. I get like so wrapped up today. Long. Fast forward. It's only a 30th by a 30th. It's only a 30th by a 30th. Oh, 30th. Why is this so hard to say? I think the sheer scales involved are really going to scupper us when it comes to like international travel. It's COVID that's scuppering international travel, not the scale of the universe. Interstellar, not international. I feel like I need a giant plate of mashed potato to talk about aliens, don't I?